What did we learn last time? Right? Last time, we mostly learned clock skew. Clock skew, say again, it is what? You have the clock going in the space, right? From left to right, from top to bottom. So it takes times to reach the other part, even it is fast, but still it takes times, right? So you will have a delay. So for example, the clock, same clock signal, no buffer. It reach here, we call it clock 1. It may have a positive edge here, right? But it takes some time, which we call it delta, which is a skew, it to reach the other register. So actually it go up a little bit later, right? So because of this, it's going to affect the equation we have, how this logic can operate, right? So again, this logic, right, when we're asking this type of question, is all based on this type of structure. We have register. So your whole CPU, it has clock. In each clock cycle, it does one computation. Then you need to store the value. Here is just a simple part of it, but it kind of represents what happened everywhere. When the clock comes up, I take the data from the previous block and pass to here, and then I let it to do the computation. And the result should not go through. For here, it already take the signal, the result from the previous computation, and pass to here already. Whatever you are doing here should not affect the next stage, right? So this is the ideal case, right? So because of this, do you remember what is the smallest clock period that we can have for the given situation? You basically is asking yourself, like, this is very important because in all the exam question, it's all based on this, right? And then you try to figure out how is this special logic going to screw up my calculation, right? So, but the idea is that I want to bring this data into here and do computation. Before this computation finish, I should not pass to the next stage, right? Just imagine as you are the old time, right, factory worker, you try to assembly a car, even nowadays, right? But you are working there. Your job is to, for example, in here, you take the frame from the previous stage, they make it, and then you assemble the wheels. And then you pass the frame with the wheel to the next stage, maybe they put in the engine. So here is they put the engine, right? But you are so mechanical. There's a very bad manager. They have a wipe, right? Once they wipe you, they need to pass it to the next stage. So, or let's don't say wipe. They just they force you to pass to the next stage. How fast can they force you? If you have not finished assembling the wheel, you only put in 2 wheels, and then they ask you to pass to the next stage, then you have a corrupted car for the next stage. Even they put in the engine, do the painting perfectly, eventually this is just a perfect car, but missing 2 wheels, right? So you need to ask yourself, how fast can the manager ask you to pass the data to the next stage, right? So do you remember, anyone still remember the equation? Although you can put in cheat sheet, but understanding is more important because basically the cheat sheet is not useless. It's useless. We are not going to ask you to calculate this. You need to understand and derive the equation, right? So what is the minimum clock period, right? What is the minimum time the manager can ask you to pass your product to the next stage without corrupting the product? Anyone? But what does it depend on, right? I give you so much data. What does it depend on?
T C2Q minimum plus T combinational logic minimum value.
TCQ, but plus T logic, but not minimum. Minimum is contamination delay. Are you referring to CD?
Yeah.
Okay, but now I'm asking the time that, right? So for example, for some products, right? For example, you're in your assembly line, you're not just putting the wheel on a car. Maybe sometimes you put the wheel on a bicycle, which is take much shorter time. That is the contamination delay, right? You can pass it very fast. But now I'm asking, what is the minimum time the manager can ask you to pass? You need to consider the maximum delay, right? Because the manager doesn't know what you're doing. You may be assembling a bicycle or a car with 4 wheels, right? So the manager need to consider the worst case, which is T logic, correct? What else besides TCQ? TCQ is just like the manager say, pass it, and then the previous stage people give you the frame. It takes some time to reach your desk. And then T logic is like you start assembling the wheel. And after that, you will pass it also, right? But however, in terms of digital circuit, we have some very funny thing called setup time, right? You need to be ready for them to fetch it. You cannot just say that when the manager say, next stage can take your stuff, then they will take it. Maybe because you need to bake the wheel a little bit, right? Heat it up, or you need to do something else. So you also need to have the setup time ready so that when the manager say pass it, then they can copy the data successfully. Make sense? Any question, right? I really hope that you can ask question now, right? Unless you are doing your project at this moment. Otherwise, make sure you understand. Don't wait until the final, right? The final, we are not just asking you to substitute number to this equation. We'll give you a very complicated logic. And then you try to derive. If you don't understand this, you won't be able to derive this one, those. Okay, so this is the minimum time that you can pass. But because of the cross skew, that will be good. Because it's just like that the manager, when he try to ask you to pass, he actually need to walk to your previous stage, say pass, then you get it. And then he need to walk across yourself to the next stage and then say take it. So it takes some time for the message to arrive. So it means that when he's walking, you can still do something, right? So from the manager perspective, looks like he can shorten the clock cycle, right? So it becomes minus delta. Okay, any questions? Okay, similarly now, go back to another thing. What is the whole time, right? You need to make sure that the previous stage is somehow that when you pass something to it, it requires you to not to change the data for some time. But what if this time, what if you can do it really fast, right? When the clock comes up, you will bring something to here, and then you do it really fast. Before the whole time over, you might overwrite the data here already. Then you violate the whole time, right? So if it is ideal, we say that the whole time needs to be smaller than TCQ contamination delay, right? Because the previous stage can pass to you very fast due to contamination delay. And then the logic delay, contamination delay, because they can, for example, you're assembling a bicycle, which is very fast. But if you do it too fast, you still have not passed your car there long enough, your bicycle arrived already, you overwrite the car, right? And then you will fail. And with this skew, the worst thing is that it further requires you to reduce the whole time requirement, because the skew is saying that I'm going to take it later. I start counting the whole time later, right? So I need to make my whole time even shorter to avoid the problem. Any questions?
So, Professor, does this mean Right, you're saying that the negative skew is good for the whole check?
Negative skew is good for the whole, correct? Because then you allow it to have a longer hold time. If this register requests you to have a longer hold time, you can fulfill it.
Okay, yeah.
So if you remember last time we say if it is positive skew, you can reduce the period, so higher frequency, but worse hold time. Negative skew, you need to go to lower frequency, but better hold time. So they are contradict with each other. Very good. Now, today we will talk about cross jitter, but before we move forward, you need to understand this cross skew. Any questions?
Professor, I have one question. If the positive skew is not good for the T hole, then the delta shouldn't be the plus here.
T hole, now this is something very confusing. T hole is the, let me ask you, if you design a register, is it easier to request for longer T hole or smaller T hole?
Smaller T hole.
You think it's easier? But longer T hole
No,
is
sorry,
more,
longer is easier.
right, because it's more troublesome for the user, right? The user need to make sure that I don't change the data, right? So if you have a positive skew, you make T hole smaller. That means it's more difficult to make it, right?
Yeah, correct. But to for the positive skew, the T hole is very small. So in the equation here, the delta shouldn't be plus here, like you put minus.
It is plus. This is equivalent to, we can see from two aspects. One is for given skew, you make the T hole requirement very strict. Another is think about this, for a given T hole, your skew needs to be very small.
Okay, got it.
Right, for a given T hole, right? So if your T hole is very large, then you cannot have cross skew, right? You need to make this so perfect, arrive at the same time. Yeah, this is a very confusing part. So I'm glad you asked, but at least you know what you need to think about when you get confused. Just think about T hole is a requirement, right? Smaller, smaller means more difficult. For designer. Yeah. Any other questions? Okay, if no, I want to just mention one thing, right? How do you find the contamination delay, right? And T-logic. T-logic is easy. What is T-logic again? It's just the maximum possible delay. Okay. Supposed to be easy. Actually, here is opposite. I kind of swap the sequence. I want to talk about contamination delay first. This is the minimum delay. What is the minimum delay in this circuit? Right? I have a logic, A, B, C, D input, and I come out with the output, right? What is the minimum delay? Well, the minimum delay will be that it go through this path, right? Minimum delay will be this red one. Right? But how do you get it? It means, how about BCD? Well, if A equal to 1, I have minimum delay, right? Because this is OR gate. If A is 1, I really don't care what happened to others, right? So in the worst case, this guy can really arrive very fast. The contamination delay is as short as the delay of OR gate 1 plus the delay of OR gate 2. Is this okay? right? When A is equal to 1. Then we are done.
Professor,
Uh-huh.
shouldn't like each gate will have a specific value for the propagation delay and contamination delay? So you're talking about just the just for A. So similarly, it will come for B, C, and D, right?
No, I am talking about the contamination delay of this whole block.
Okay.
This is like the combination logic, right? We are finding the TCD and T logic. We are finding these two values for this whole block. Yes, each of them have this, but at this moment, I'm only care this whole block because this one might be sandwiched by a register. Maybe like this. Okay, because this one is what we need to find in order to figure out what are the maximum clock period we can have.
So for calculating the TPD for this, you will take the path which has the maximum gates. Is it correct?
TPD? No, for TCD, CD is the shortest one. T logic is the longest one.
Okay. Okay. Yeah.
Okay. Now, that's good, right? So easy, right? For contamination delay, because we see that if A is equal to 1, right, then it will just go through all of them, right? But what is the maximum possible path? Right? The first thing you will think is, wow, maybe B, and then N1, N2, N3, and then all. So 5 gates, pretty long, right? This is the maximum logic delay. But this example just to show you that it's not that trivial. It is actually shorter because you need to think about the logic, right? If A equal to 1, then no matter what value you have, right, the delay, the T logic is just like what we say earlier, T or 1 plus T or 2, right? Because this is an OR gate. So if 1 goes in, this one will be 1, this one will be 1. I'm not going to affected by this, right? So this is the, looks like T logic equal to this, but we want to find the maximum. So we don't think A equal to 1 is the case that gives the maximum delay. Then we just keep going. This is just because we already know the answer. Then we try to analyze in this way. If A equal to 2, A equal to 0. If A equal to 0, then you see that it really depends on this signal, right? Because this OR gate really, I need to depend on this signal. Then I have two situations. B equals to 0, okay? Now, if B equal to 0, then what will happen? This I call it, let me change the color. Green, right? It will be easier to see. Now your A equal to 0, so it has no effect. B equal to 0, that means this is 1. If this is 1, this is going to be 1, right? Then again, the other one has no effect, right? So when B equals 0, I don't care about other logic. The delay is TI1 plus TOR1 plus TOR2. This is the situation, right? Now we have the last possibility, right? Because all the possibility is I start with A equal to 1, we're done, very short, we don't think it's the logic, the maximum delay. A equal to 2 and then B equal to 0, that is one case, it gives us this. Then what if A equal to 0 and B equal to 1? We have everything already, right? We cover all the possible cases. It means C and D can be anything else if I can conclude from here. If B equal to 1, then it means this is 0, right? Now then A is 0. It means this one is 0. Then it means what? It's going to depend on this path, right? So this one will go in. It depends on this path, but this is 0. Remember, this is 0. So this path has no say. When this is 0, this is for sure 0, 0, right? So this is 0, going to be 0, right? So you see that the shortest path is going to be I1, OR1, N3, and OR3, right? It even does not go through N1 and N2. Do you see that? Just because of the logic, right? So T logic equals to TI1 plus TOR1 plus TN3 plus TOR2. Let me check it's correct. Right? So that's it, finish. So this is the longest path. It turned out this is the longest path. We cannot just look at the logic and say that, oh, this one is going to be I1, N1, N2, N3, or 2. It's because of the logic itself. You just cannot, this path just does not affect the result. If they don't affect the results, they won't affect the logical delay. That's why it's I1, OR1, N3, and O3. This is the T logic. Right? Maybe a little bit confusing, right? Let me know if you have any questions. Okay, the message here is just to say not as straightforward as visually, right? We need to analyze the logic carefully. So turn out for this logic, we can clock it at a higher frequency. Instead of just considering 5 gates, actually 4 gates will be the maximum delay. Okay. Now then, let's continue to talk about the clock jitter. What is clock jitter? Now we talk about skew. Skew is saying that you have a constant delay spatially. Okay, this is skew. This is a spatial variation, right? From one point to another point, the clock arrives at different time. Okay, jitter is that from time to time, okay, the clock arrives at different time. This is just because the non-ideal situation of many things we would mention briefly later, right? But it is very reasonable. You will think that, for example, yourself can be a clock, right? You clap. Let's let you clap, 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 clap. This is a clock already. You can use this to control people's movement, right? As a team or the conductor. The conductor is a clock itself. And we expect the conductor trying to, right, wipe his conductor for a certain beat every second, right? But if you really measure it accurately, it won't come up exactly at the same time. Sometimes a little bit earlier, sometimes a little bit later. That is just the nature, due to noise at least, right? So clock jittering is talking about the same clock coming into the same register, but they don't come at the expected time. For example, 2 and 5 at the ideal time. Maybe at 1 second it should come up, 2 seconds it should come up. That's a 1 hertz. But sometimes it come up a little bit earlier, sometimes later. So this is a random variation. It's a temporal random variation. But no matter how random it is, there's still a worst case, right? Just like the conductor, no matter how lousy that conductor is, it probably won't have a jitter more than 1/10 of the clock period. Otherwise, the song is going to be completely out of shape, right? So maybe they will say, oh, the clock jitter, absolute lowercase jitter is, let's say, 1 picosecond, 0.1 picosecond. Okay, but we can also have a jitter that is talking about another is this is the measure of the worst case jitter you have. And then capital 1 is cycle to cycle. So from this cycle to this cycle, what is the jitter? Right? We don't know. It's again a random variable. But let's say this one come up at this point, and the other come up at this point. We subtract the clock period, just the difference between the clock period, right? For example, 1 second. For example, this may come up at 2.01 second, right? This may come at 0.99 second, and I expect the clock period to be 1 second, right? So the clock jitter, right, is going to be how much? 0.02 second, right? It's talking about this one, right? So what is the worst case jitter? Well, the worst case is you really come up very early in the previous cycle, and then you come up very late in the next cycle, right? This is basically the worst case. Right? And what is this? Can you let me know what? This is not the worst case. Actually, the distance, I need to minus the clock, right? What is the worst case, worst value for this? Based on this figure. If it is 0, then it's perfect, right? But what is the worst, biggest difference between T jitter and T clock? Like this one come up about T jitter, lowercase t jitter earlier. This is lowercase t jitter later, right? So the worst case is going to be 2T jitter. Make sense? Is that okay? Now, since we are comparing the same register, we use this logic. Okay, so there's a feedback after this combinational logic, right? So what is the maximum clock period I can do, right? This is just like I do everything myself. I build the frame of the car, and then I put on the wheel, but I need to have a clock, right? Very regular. So again, the manager going to force me to do the next step, cannot force me to do it too fast because I don't want to put in the engine before I finish putting on the wheel, right? Etc. So what is the maximum period that I can do? The minimum period or maximum frequency that I can operate. Same, right? I need to, although this comes from myself, but still it's just like going to the other person. Clock to Q. First, I need to take the previous data to here, plus my logic delay. Again, I need to have the correct setup time so that I can go to next clock cycle to copy it, right? But now I don't have skew because I'm the same register. However, I have clock jitter, right? Now the clock jitter is this. I don't know positive or negative because it's a random number. So what do? I take the worst case. Once I take the worst case, it's just like cross skew. I just take the worst case cross skew. Okay, so this will become 2T jitter. Because the worst case is that the first clock comes one small T jitter earlier, the second clock comes one small T jitter later, right? So this just like the cross skew. The difference is like 2 jitter. So I need to have this plus, right? As if delta equal to negative 2 jitter. Is this clear? Any questions? Let's pause for half minutes. Think about that. So I feel this one, right? If you have learned machine learning, it's a little bit like the recurrent neural network, right? We can unfold it. For example, this one, you will become something like this, actually. You can even imagine this one as a clock going in, right? And then let's call logic A. And then you go here, but you keep going, still logic A, right? We unfold the recurrent neural network, right? And this is clock. The only difference is that now this clock has no delay. They are the same, no skew, right? But has jitter, right? Which is equivalent to skew, right? Unfolding. Like recurrent neural network, if you learn machine learning before, right? So then it will be easier to understand, right? You just pass, although you are the only one, you are still the one who do everything, but you just pass it to yourself. You have many copies of yourself. You still need to obey all these things, right? So that's why then it won't be difficult, right? If you understand the cross skew, now you understand that, hey, this is just like I have a cross skew equal to -2 jitter, because I'm looking for the worst case. Jitter can be positive, can be negative, and I never know where it is because it's a random variable. Just like the conductor, as I said, the conductor won't be exact when you wipe the conductor. I assume that is called conductor. The rod. What do you call the rod, right? So similarly, if this is the case, even without understanding, you will know that hole, right? Smaller is worse, right? It's going to be smaller than T call to Q contamination delay plus T logic contamination delay. And I want to make it worse because as an engineer, you always look for the worst situation to safeguard the worst situation. What can make it worse? It must be making T hole smaller, right? So I -2 T jitter. And here is what? As if the delta is 2 jitter, right? So before you see that, if you're talking about the skew, they will have the same sign. But now it's different because we're looking at the worst case condition. Sometimes the skew is positive, sometimes the jitter is more positive, sometimes it's more negative. When it is more positive, it actually, I don't know what is the meaning of positive actually, right? It's in one side, it reduces my frequency. On the other side, it makes my whole time requirement more stringent, right? So I take the worst case. So no matter what, when you come with the random variable, right, in the future, you design different things. Just like when you design a circuit, you know people talk about the corner. We don't have the corner design in this class, but you learn that in E223, right? You do a lot of corner. You try to see have fast, low, or fast, low. Right? Usually you don't care about fast, low, or low, fast, right? If both NMOS and PMOS, but they can be the worst case actually, right? But let's say both are low, both are slow, both are fast, right? It can happen that the PMOS is faster, but we always look at the worst case, just like here, okay? Any questions? If no, right, then eventually what we can do, what if yours has both skew and jitter? It's just equation, but the point is that you just put them into it and then you will I mean, you understand what I said earlier, it won't be difficult. Let's start with clock period, right? When we say period, we're of course asking for the minimum period because that's what we care. We want to increase the clock frequency, right? The period needs to be larger than something, means the frequency needs to be smaller than something. Just start with the skew equation. TCQ, again, I need you to copy when the clock comes up, and then go through my logic delay, right? And then I need the setup time. Maybe let me write a little bit. I don't know if this will confuse you or help you. This is called TCQ. After this, you go through T logic, right? And then here I need a T setup. Only after this is done, then come another clock, right? Then I go to the next stage. And we just say that with skew. What is the equation? Let's say I have a positive skew. It means this one come later. It allows me to have a smaller clock frequency, right? Minus delta. If you forgot, cheat sheet, right? Google, whatever. Now, if I add jitter, we know the maximum jitter is 2T jitter, right? The maximum one, equivalent to a skew, right? Is 2T jitter. Are you going to add 2T jitter or subtract 2T jitter? What will, let's say you forgot to copy this equation in the Excel, right? Is it going to add or subtract? And think about this, the nature is always working against us. You can say that, right? Otherwise, we have all the free resources. So if there's jitter, which is imperfect, is it going to make your clock frequency higher or lower? And just ask why your employer want to pay you so much every year just to design the circuit. Of course, you want to solve the problem, right? So adding jitter must be making the period longer, right? Jitter is hurting us. So we think about the worst case, right? You can either have the equation be ready or think it this way. It cannot be minus T jitter. How can the randomness or the ideal situation actually make our life easier? Then we don't need engineer. We just mess up the chip and it will run very fast, right? So because of the worst case condition, of course, you can then think about what exactly it means, like what we say earlier. When you have this clock with the delta from one place to another place, and then suddenly you have jitter. For example, you come here so early, and then the second clock come up so late, right? So this is basically talking about we have a delta, right? This is the delta plus T jitter. And then here also T jitter, right? This three all together becomes delta plus 2 T jitter. Okay, any questions? But of course, this one you will get confused because of the way I draw it. This is more like negative T jitter, right? Because it's going in the opposite direction. Okay, then how about the whole time? We just repeat what we did earlier. It has to be smaller than T clock to Q contamination delay plus T to logic contamination delay. And then if you have the skew, it's still negative. Look at the sign. They should have the same sign, right? Negative make this one better. Negative make this one worse. But they have the same 2T jitter because as we said earlier, right, they are the worst case. Right, so for example, I can look at the delta, right? Let's say you are given T clock to Q contamination delay, right? You're given the T logic contamination delay, right? You're given 2T jitter right? And then you know the T-hole, right? So basically this is what someone tell you, okay, my contamination delay is 1 nanosecond for the clock to queue. My contamination delay of the logic is all 1 nanosecond, okay? But I have a T jitter. Okay, did I say something wrong here? This should be negative 2 T jitter, right? Because we want to make it worse. Right. My T jitter may be 2 of them, maybe also 1 nanosecond. Okay. But it is 2. And then this is 1 nanosecond, right? So your your design team gave you a T hold that is 1 nanosecond, saying that you need to hold for 1 nanosecond. And at the same time, your design team also tell you that our clock is pretty lousy. It has 2 nanosecond jitter. And then you realize that another team say that their clock T to Q and also logic contamination delay is 1 nanosecond. So all this combined together equals to what? Negative 1 nanosecond. So basically, and you are the guy, right? You are the one routing the clock. What will you do? You say that the clock skew should be negative 1 nanosecond. Is it possible? Any suggestion? How will you solve this problem? We come from different team, right? Right. This one comes from the clock designer. Right. They said that's the best I can do. This comes from the register designer. Right. And this comes from the logic designer. And you are routing the clock. What will you do? Any suggestion? Is it possible, first of all, can I have a negative skew? Okay, anyway, right? So this is not possible, right? Because if you're routing it this way, but you can have a negative skew by routing the clock opposite to the logic flow. Remember, your logic may be going in this way, and your clock will go from here. Right? So in this case, you can solve this problem. But for simple logic, you can do that. Last time I showed you, mostly you cannot do that because there will be a looping, there will be a feedback. Okay, any questions? So what are the possible source of skew and jitter? Your clock can be not ideal, like the quartz, right? They fluctuate due to noise, thermal or other things. Your device, your device can have some imperfection. Sometimes some devices go faster, some are slower, right? Power supply can be changing because of the IR drop, right? Like here, IR drop. Then you don't have the correct voltage. Sometimes you suddenly draw a lot of current, so you have more IR drop. Then your delay will increase, right? Interconnect because of the capacitance, but most importantly, it may be switching because when it is switching, then your capacitance can go up and down. I'm going to show you. And that can cause skew and delay and jitter, right? And then the loading can be changing, capacitor can be different, right? So let's look at this. What are the major source for skew? Skew means that you have a constant delay. Right? Basically, it's constant. It's just because of the imperfection, right? So including the device, when the clock, this is the clock, right? It go through this buffer, it will have a delay. Interconnect also, a pretty constant delay, right? But it can be varying. Okay, and finally is the temperature. So why we say temperature is a skew? Temperature can change, right? But because temperature has a very large time constant. So basically, it is, you can say is constant in the time we are considering. For example, you can take 10 seconds to change from one temperature to another temperature, or even doesn't change, you just have a steady temperature, right? And because of this, then your chip have different temperature, so you have different resistance and different delay. Okay, for jitter, obviously, one is the cause, right? The cause, it has a jitter, right? That's why we need this phase lock loop. We are not covering here, right? 4 is the power supply. In particular, power supply is because the IR drop, and I depends on activity. Right? So this is something we cannot predict, right? Who knows what the user is going to do? Maybe the user is just watching movie the whole day, or the user is only checking email, or the user will check email and watch movie, check email, watch movie. All these are unpredictable, right? So they can draw a lot of current or a little bit current, right? And 1, 2, 5, 6, capacitive load, right? And also the coupling. And you know, capacitance really depends on the bias situation, right? Remember all those MOS capturing and gate capacitance, they keep changing, right? So they will cause a jitter, okay? Any questions? If no, right, let's see how I can minimize the impact, right? One is that we try to have a tree structure. This one go in and then separate into 2 branch and go into 2 branch. So you will see that to reach this point, it arrived 1, 2, 3, 4, 5, right? How about this point? Also 1, 2, still equivalent, 3, 4, 5, right? If I call this A, B, C, D, E, I still have A, B, C, D, E. So by doing a very good layout in the clock, I can deliver my clock through the chip pretty uniformly. Okay, and then when you reach this local region, you cannot do that anymore, but the delay won't have a big difference. Okay, another is RC matching. Why I want to do this? If I have more resistance or capacitance here, I expect it's going to take more time. In that case, I should make it shorter. So here is that for each branch, you try to match the capacitance and also the resistance so that you have the same delay. Okay, so difficult, right? And I don't think you're the one going to do that. The EDA tool from Synopsys and Cadence is going to do that, but you need to know what they are doing so that you also want to put your logic to let them route easier, right? You don't try to give a bad problem for them to solve. Another possibility is, hey, I have a grid system. This is actually very energy consuming, but in some cases it's useful, right? You have the clock coming from everywhere, and then you have this grid. So you almost have no RC drop, no no with IR drop, right? Because they can access everywhere. It's just like what? Just like, let's say in San Jose, right? They have this power grid delivered from the power plant uniformly. And then whenever they see a house, they drop a line to your house and they power up your house. In this case, all of you can access the power pretty much the same, right? Unless now those who are closer to the electric plant can get it easier, and those further away need a substation to do something, right? That's my guess, but that's an analogy, right? But most important is more allows the last minute change. I don't know if you heard about this. That is called engineering order. I forgot the exact name. That is very important. When your team take out a chip, start from scratch, and your goal is to get it done in 4 months, and you need to tape out tomorrow or the day after tomorrow, and then you find a bug at the last minute. You already generated all the critical mass, most of them, right? So what do? That is 100 million project, right? You scrap it, your company will be in a big trouble, right? Even Intel, 100 million is something, right? So what you can do is do some last minute change. Because you have this grid where it's very easy, just only take the last metal layer and only change the metal layer because they are connected everywhere. So I can easily reroute it, just change one mask. And this come from the approval from the VP. The VP say, okay, do this, right? So that's why it's like order, change order, something like that. Forgot the name. Yeah. So this allowed the last minute change because the clock is so easy to access. Unlike this tree, if I deliver in this way and then I find I route it wrong, the transistor below a lot wrong, then I need to change many layers. But now it's everywhere. It is very easy to me just tap into another power supply. Okay. Any questions? If no, then let's go to crosstalk, right? Let me, because this, of course, related to the clock, why the capacitance is causing the jitter, right? But here, this crosstalk also related to dynamic logic. So let's just quickly review. What is, if Y is faulting, right? What is the capacitance on Y? It really depends on the voltage on X. It's just a capacitance divider. So we say the delta voltage at Y, right? You just use voltage divider, 1 over Cy divided 1 over Cx plus 1 over Cy. Cxy plus 1 over Cy, right? Because this is just effective impedance, right? If you put into the frequency domain. So then you give out Cxy divided by Cxy plus Cy. And this Cxy is the coupling cap. We always say coupling cap. And you see that if the coupling capacitance is large, whatever is changed in X is going to affect Y. Okay? Here is an example, right? We might have this dynamic logic, right? At this stage, maybe this is off. And this is during the evaluation. We want to keep this, for example, at, let's say, 2.5 volt. It was at 2.5 volt. And now you have a line running across it. It has a coupling capacitance Cxy, right? So what will happen? Then Y delta Vy, as we said, equal to Cxy divided by Cxy plus Cy, which is equal to 6 femtofarad divided by 6 femtofarad plus 0.5 femtofarad, right? And I forgot to put delta Vx. And this delta Vx changes from 2.5 to 0. So it's negative 2.5. So what is this? It gives a negative 0.35 volts. Okay, so I mean, this is the delta, okay? So it means Vy change from 2.5 volt to 0.65 volt. Okay, what's the problem? Then, if this is C, then Vc will go from 0 to 2.5. And then corrupt the next stage. Right? Because the next stage was expecting 0. But because of this coupling, this becomes 2.5. And then the next stage will get discharged if it is a dynamic logic. And then everything is gone. Right. Any questions? Is that clear? So how can we avoid this? Almost impossible. We try to reduce the crosstalk, but we also want to see what is the situation that make it worse, right? It's impossible to have it completely floating. Even in this case, you have some finite resistance, right? Although not infinity. And you will see that the point is that if Ry is small, right? That is easy to understand. If Y is tapped to a certain voltage, you can never change it. If it is floating, Ry is very large, you can change it a lot. Okay, so basically, this depends on Ry, and at the same time depends on the rise time. This is time, this is Vx, and this is the rise time of Vx. If you Vx do it slowly, this one can catch up, right? So you can see that if I have a longer rise time, this is Vy, then you won't get disturbed so much, right? If you have a very huge, very fast rise time, you would disturb this a lot. You would disturb the Y a lot. Okay, so our goal is to have the rise time, right, much larger than Ry times Cxy plus Cy to avoid crosstalk. So this is just the feeling I hope that you can get, right? One is that you either tie this node stronger to the VDD or ground, then I cannot change it. Or this signal goes slowly. But this all against what we have nowadays. The signal is so fast, the coupling capacitance is so large, so we will have a lot of crosstalk that you need to pay attention to. Okay, any questions? Now, so how do we reduce the crosstalk, right? Can you let me know? If I increase the signal swing, is it going to reduce the crosstalk? No, right? You have a larger delta V, right? Delta V, so more, right? So this doesn't work. Okay, how about floating 9? We just discussed. If you float it, again, you will have more crosstalk, right? So you need to avoid the floating 9. Okay, so this will help avoid the floating 9. Right, just connect them to ground or somewhere. Right, and as I said, reduce the rise time will reduce the crosstalk. Okay, and by the way, this one you can use the keeper device. I forgot to say that. Do you remember the breathing device in the domino logic? In the dynamic logic, Prudan network, right? What we did is to add something like this. Do you remember this one? If this is 0, this is 1, this is 0, yeah? This is the keeper, right? If you forgot, go back to read the previous slide, okay? Differential signal will help because they will go up and down at the same time, then we are not affected by them, right? Parallel wire is bad, right? Because it's large cap. It's going to be large. The coupling cap is large. Okay. Or you can use shielding wire, then you can avoid the crosstalk. For example, here, I have some signal here. I add a VDD plane here. We call it ground plane. Then the signal cannot go through. And I can avoid the crosstalk. Okay. And finally, of course, you can add ground plane also, but you increase the capacitance, which means you increase the power, right? And you increase the or area, which we don't want from PPAC perspective. Any question? I'm a little bit too fast, but this should not be too difficult. Any questions?
Professor, so this is regarding the clock.
Sorry, say again. Actually, this one I say the wrong thing. Can you say again regarding what?
So this is regarding the clock.
Yes, it's related to clock because clock has the most trouble, but it also related to signal. And mostly,
Professor, my question is regarding the clock design basically. So whenever we have a full chip thing, so where we have analog systems and as well as digital systems, where the PLL generates the clock. So how do we design the clock in such cases?
how do you decide the clock? You just need to avoid all these things. For example, do not run your clock in parallel with the signal, right? And for example, rise time probably you cannot change much. If you can have differential signal, you use differential signal. If you can get a ground plane to show it. Otherwise, yeah, it won't work. Your circuit just fail. Do I answer your question? I don't know if I answered.
No, so this is not related to the crosstalk. What I'm saying is like, so with respect to the design considerations, so generally, how do we design the clock whenever we have both the systems? Like we, for digital systems, we generally consider all these propagation delays and everything.
Yeah.
So, but for whenever we have it for analog and digital systems, so how do we design the clock, and then what are the considerations that we need to do?
I don't know. I'm not expert, but I still don't know exactly what you are asking. So you mean you have an analog system and also a digital system, right? You want to separate them as much as possible because digital system has a lot of noise and the analog system doesn't like the noise, right? So you want to separate them. And your clock should not run over the analog because they don't need the clock. Try to avoid to first of all, I'm not expert. I'm probably not good enough to answer, but do I answer your question or you actually have more detailed question?
No, my question is somewhat different. Like whenever the clock is being used by an analog system and as well as a digital system, let's say. So what should be the frequency of the clock, and then how do we consider the skew, and then how do you consider the jitter? So if both the systems uses the clock, let's say if PLL is generating a clock, let's say for some frequency. So how do we consider the clock, jitter, skew, everything whenever we have both the digital and analog systems?
I don't see. Are you saying that if you have both analog and digital, how is it compared to just having digital when you design the clock?
Yeah, somewhat.
I don't know. Maybe I just cannot answer. I'm not able to answer this question and intellectual. I mean, in my knowledge. So I mean, you just need to think about I mean, designing the clock. This is a very big problem, right? The point is here. I try to say that you need to avoid this crosstalk issue. In digital, for example, you use switch capacitor, and that clock maybe something more complicated need to think about for digital switch capacitor. You worry about all this matching and also the I don't know, the jitter and skew might not be a big problem because you're not doing register. You see what I mean? Because for digital circuit, when you use this clock or something, it's less important. Jitter may have the noise, but maybe I'm wrong, but it's less important in terms of jitter and skew for analog. But if you put between the register, then it becomes important. Okay, let me say this. Maybe I'm not good enough to answer this question. I don't have experience. But what I'm saying is that at least you need to fulfill what I'm talking about here, right? If you have register, you're doing the clock, the most important is the register, right? You need to copy the data. There are two things, right? One, you don't corrupt the data in between. That is the noise, all this coupling. Second, you need to meet the timing constraint, right? And then if you say you have analog circuit, then you think about why you have a clock in the analog. Right? Sometimes, for example, you have the switch capacitor. But for switch capacitor, then probably, I don't know, maybe the skew and depends on the accuracy, right? Your DAC, ADC, if you have some skew, if they can FH out, maybe that's not a big deal, right? That's what I think. Yeah, probably that's all I can answer. Okay.
Okay, thank you, Professor.
Okay, so why I say that there is a jitter due to the capacitor, because the capacitance you see is actually not constant, right? I have 3 voltage here, right? Vx, Vy, and Vc. Okay. Now look at what is the capacitance seen by Y? If Vx is flat, Vc is flat, and then Vy goes up, right? Then, well, I have ground X, Y, and Z. Then, of course, I think I will see 2Cc, right? Because they all grounded, so I do see 2 capacitors. But if the signal is such that the Vx is going up, Vy is going up, Vc is going up at the same time, what capacitance do I see? I don't see any capacitance because the delta V across Cc is 0. Or let me just say unchanged, because we have different definition of delta V. Right? If you don't change the voltage across the capacitor, you don't need to charge anything. You don't need to deliver charge. So there's just no capacitance. And similarly, what if Y is going up, but Vx is going down, and Vc is going down at the same time? Then you will see 4Cc, just due to the Mueller effect, right? Which we discussed before already. One goes up, another goes down, right? The voltage across it changed by 2V, but from Vy perspective, it's only changing V. But you need to supply the charge to change 2V. So it looks like the capacitance is larger, right? So this definitely caused a lot of jitter, because the signal is going to delay or faster or be faster, depends on the activity of other logics. Is that okay? Okay, now, so if that is the case, right? So we need to pay attention to this large capacitive loading when you design the clock. The clock, the most difficult, yeah, you have this jitter, whatever, that is important for accuracy. But first, you need to go through this delay, large capacitive loading first, right? So what are they? The buses, the clock network, right? That's for clock. And then off-chip loading, right? You might try to load some very large capacitance off-chip, right? Control wire set reset, because you have the one set, right? Connect to many memory at the same time. Right? So how do you size the transistor? We know that already. First, distribute the delay equally in each state. If it is a buffer, we say that we make Fi equal to constant, remember? Right? And fan out equal to 4 is the best. We already learned that before. So let's review. If I have an off-chip loading is 20 picofarad and intrinsic delay is 2.5 picofarad, how should I size it? Well, midterm question. F equal to 20 picofarad divided by 2.5, and this is 8,000. Okay. And then I decided that maybe I want to use gamma, let gamma, right, equals to 1. Yeah, I use fan out to 4 because I already say that fan out to 4 is the best. This is like what you did in your assignment, right? Then it means F equal to 4 to the power n. So with this, you get n equal to 7, okay? But of course, this is not exact, right? This is not exact, right? So we say about 7 stages, right? the exact solution will be, we start with this 7 stages, then we say, okay, maybe f, let's set f to the power 7 equal to 8,000. Because we cannot have discrete stages, we say 7, right? Because 7 for fan out equal to 4, give out the best and give out the exact f equal to 3.6, right? You know how to do this already. I won't spend too much time. But the main point is this. Then what does it mean? The first stage, right? I might have the W equal to 1 micron. Okay. Then what happened to the last stage? Based on this, it will be 1 micron times 3.6 to the power 6, which is 2 millimeter. Wow. Can you afford to just make the buffer train with a 2 millimeter size inverter that you can see, 2 transistor, 2 millimeter? Impossible, right? Then it means this doesn't work. But on the other hand, it's very often we need to ask ourselves, is this is what we need? Maybe we don't need to meet such a stringent requirement in practically, right? Maybe all we need is just that we want to meet a certain requirement. So this is the delay given by maybe your vendor or your customer. Your customer or your customer can be a team in the company. The customer just say that, okay, yeah, you need to drive this large capacitor, but you don't have to minimize the delay. All I need is just you have the delay with, let's say, 100 nanosecond. Then try to minimize. Then how do we size this one? Okay, how do we size this one? So I'm not going to derive it, but basically it has an equation. This is the intrinsic delay. What you want to do is that you size it so that T P max divided P0 equal to n times f to the power 1 over n. And this is the plot of this equation. Okay, so for example, if I decided that my delay has to be, let's say, 100, right? I found that the TP max divided by TP0 is 100 because they say I don't need to go too fast, but at least my times cannot be more than TP0 equal to 100, right? And then based on the fan out, it is, let's say if fan out is 10,000, right, or 8,000. If it is 10,000, then you see that if I can make n equal to 3, I meet the requirement. So I really don't need to do 6 stages. You see here, I need to use 6 stages, but no, I just use 3